Hello everyone, this is a recap of the severe weather event that occurred on Thursday evening, May 28, 2015, to the east of Iron Mountain, impacting Quinnipiac, Norway, Vulcan, and Waseda. This information is presented by Jason Allenbaugh and Keith Cooley from the National Weather Service office near Marquette. This is the first severe weather review we've completed in this format, so we definitely welcome any feedback from this severe weather review. So what happened with this event? Well, we had 3 supercell thunderstorms that produced quarter to golf ball size hail across southern Dickinson County. Now what makes this event fairly unusual is that they impacted the same areas within a span of 3 to 4 hours. The rest of the UP had only a few spotty showers and thunderstorms, but nothing as extensive as these storms. The main reason the storms over southern Dickinson County were much stronger and focused to that area was because of the co-location of warm, moist air and the boundary from Lake Michigan modified air. This lake breeze boundary allowed for increased wind shear, causing the storms to intensify rapidly. This increased wind shear allowed hail to remain aloft much longer, producing increasing hail sizes. Additionally, the rotation in the storm allowed a few funnel clouds and wall clouds to form, one of which is shown here in this image. As previously mentioned, there wasn't much going on across the rest of Upper Michigan except for maybe a few unorganized showers and thunderstorms over the west half. As this radar loops, you can definitely see the training supercells across southern Dickinson County. One thing to note here is that there is a longer break between Storm 1 and Storm 2 than there is between Storm 2 and Storm 3. The extended break between storms allowed the atmosphere to become even more unstable, allowing the next 2 storms to become even stronger, producing the golf ball size hail and funnel clouds. We will get into the details of each storm as we get farther into the presentation. So once again you can see as our loop starts up here again, there's the first storm moving off to the east and dissipating, a longer break, and then here's Storm 2, stronger, third storm very close behind. After looking at radar imagery, we'll now take a look at rapid scan satellite imagery. This is a new high temporal resolution satellite product that allows us to see minute-by-minute satellite data from select portions of the country. On this day, we were very fortunate to have it focused on the upper Great Lakes. The first thing to notice here before we loop the imagery is that the first severe storm was dissipating and lifting off to the northeast of southern Dickinson County. And you can see that right here. Here's the first storm. Now the big thing to notice as we start the loop up is that there was a lengthy break in the cloud cover between the first storm and this second storm. This allowed prime conditions for the atmosphere to become very unstable ahead of that second storm. And now here comes the third storm right after it. This will loop one more time, and we'll get to see the whole thing again from the dissipation of the first storm through the second and the third storm. Here's the first storm moving off to the east and dissipating, and then there's the break, and then here's the much stronger second storm. You can see the anvil cloud actually spilling all the way over into northern Lake Michigan off of this storm, and then here comes the third storm. Now Keith is going to focus on each storm with more detail.
Now we will zoom in a little closer and see what happened with each of the severe thunderstorms. This is an image of the first severe thunderstorm warning that occurred a little after 4 p.m. Central Time. The blue outline is the area under the greatest severe weather threat. Keep in mind that severe thunderstorm warnings are issued when hail greater than 1 inch in diameter or quarter size, or wind gusts 58 miles per hour or greater are expected. Another thing to note about this graphic is that the storm was moving very slowly, at around 10 miles per hour. This allowed very heavy rain to occur across much of the outlined area as well. Here are some of the reports received from this first storm. The largest hail that we had reported with this storm was around 1 inch or quarter size, and really no reports of damaging winds were received. This, however, was only the beginning of a bumpy afternoon and evening. This is an image of the second severe thunderstorm warning that occurred a little after 6 p.m. Central Time. Again, the blue outline was the area under the greatest severe weather threat. Notice that this storm was taking a similar path as the first storm. While this storm was moving much faster than the first storm, the training motion of the storms began to cause flash flooding concerns, and we began to receive several reports of standing water on area roadways. Unlike the first storm, this second storm had multiple reports of wall clouds and funnel clouds. This makes sense as the radar imagery in the top left shows the hook feature to the south of the storm, which we associate with the supercell structure. It is in this location that we expect to see the wall cloud, funnel cloud, and tornado as shown in the top right diagram. The picture shown in the bottom right corner is a view from near the hook-like feature on the south side of the storm, around the same time as the radar image. The wall cloud is very evident in this image, kind of right in that location. Here are several more images that are submitted to our office via the National Weather Service Facebook account. Again, most of these look very ominous, but it's hard to say for sure if any of these are rotating by looking at the still images. In at least one of the images, the bottom right, the individual that submitted the report mentioned that the cloud appeared to have some rotation in it. This is a very good thing to mention when submitting the report, as we can pass this along in our warnings and updates, and it gives us a good idea of what is going on in the lowest levels of the storm. Another thing to note is that the storm was very visible from the Negaunee area, as shown by the image in the top right corner, indicating that the storm was fairly tall. Additionally, the storm had Peleus clouds above it, which is another good indication that the updraft is very strong. Now if you take a look at that image closely there, you can kind of see those clouds that are above the cumulonimbus cloud. So why would the second storm produce all the ominous cloud features and increase severe weather reports? Well, one of the biggest reasons that this happened was the large break between the first storm and the development of the second storm. The moisture left behind by the first storm, coupled with the increased heating from the large break in the cloud cover, allowed instability to increase significantly. A lot of this increased instability was rooted in the lower levels of the atmosphere, which is what we would need to begin seeing wall cloud formation and funnel cloud formation. This will be discussed in more detail in the next couple of slides. Before we get to that, we will jump back to the radar loop once again to see the longer gap between the storms. Notice how there is a larger break between the first storm and the second storm than there was between the second and the third storm. As we see this loop here, we can take a look at that a little closer here. So here's the first storm moving through, and then this long break, then the second storm pops up, which was much stronger, and then the third one followed quickly behind. That really helped to re-energize the atmosphere before the second storm developed. The warmer and more moist low-level environment left behind by the first storm allowed the base of the second storm to develop much lower in the atmosphere. This storm base is represented by what we call the lifted condensation level, or the LCL. As the LCL or storm base becomes rooted lower in the atmosphere, the chances of seeing a wall cloud, funnel cloud, or tornado begins to increase, provided that enough instability and shear are around to produce them. A good example of high base storms versus low base storms can be seen by comparing the images on the right side of the slide. The top image has a much higher base than the storm in Dickinson County, shown on the bottom right image. Now for the last but not least of the severe thunderstorms. This last storm moved in almost immediately after the second storm, again over the same areas as the first two storms. The LCL was likely still low with this storm, but the atmosphere had been worked over a bit more before the storm moved in. This basically means that the storm had a little less instability to work with than the previous storm. That doesn't mean that this storm wasn't still strong, because it did actually produce large hail. It just means that the proper balance between shear and instability was not there to support the stronger rotation that we saw with the second storm. Now here are some of the reports submitted to our office from the third storm. Again, all of these images were submitted to our office via the National Weather Service Facebook page, while some of the typed reports in the center of the page were called into the office. There are two things to note from these images. First, notice how the hailstones are clumped together. This is caused as the hailstones are tossed around in the storm. As the smaller hailstones bump into one another, they freeze together, which causes this clumpy appearance, along with the appendages protruding from the sides. Second, the images each have a reference in the background to help identify the hail size. For example, it is very easy to see that the hail in the top right image is quite a bit larger than a quarter. It can be difficult to see this without a reference object. Nearly all of our reports had reference objects or mentioned the hail size directly in the reports we received, and all of us at the National Weather Service in Marquette want to send a special thanks to everyone that sent in reports from each one of these storms. Again, these reports are very important to us and are greatly appreciated. Now Jason will finish up with a quick review of Storm Spotter pointers and tips.
We've added a few slides here at the end of the presentation to give spotter information to those that may be interested in sending reports to the National Weather Service in the future. What are the basics we would need? We need to know what severe weather you're seeing, where you're seeing the severe weather, and at what time when it happened. All of this information can be sent in via social media or also on our website. When reporting hail size, it will probably be easier for you to reference pocket change or your favorite sports ball, as much of us don't really carry a ruler with us. One thing we always try to mention to our spotters is that we try to stay away from marble-sized hail. And why is that? Well, it's because marbles come in multiple sizes, which makes it hard for us to determine how large the hail actually is. Wind speeds are probably one of the most difficult types of severe weather to estimate. This is largely due to the very scary appearance of the wind-driven rain, along with the thunder and lightning that are typically involved. This causes us to generally overestimate how strong the winds actually are. The main thing to grab from the list provided here is that winds are probably not reaching severe criteria until they are in the 55 to 72 mile per hour range or greater. That's when you'll begin to see some sort of damage, usually in the form of large tree branches snapping off or other forms of structural damage. Any winds lighter than that will typically cause little to no damage. There are multiple ways to get the information to our office. One way is to submit the report via our website, shown at the top of the list here. Once that report is submitted, an alarm goes off in our workstations in the operations area right after that's submitted to our site, so we'll get it very soon. We will walk you through this process in the next slide, as it may have changed a little bit with the latest changes to our website. Additionally, we always have someone dedicated to monitoring and communicating through Facebook and Twitter, which has been one of the most utilized ways of getting reports over the past couple of years. Another source is ham radio. During larger events across our area, we will have a ham radio operator receiving reports across the radio. As previously mentioned, we'll now explain the process of submitting reports through our website. To submit the reports via the website, you just have to mouse over the Current Hazards tab on our homepage. Once you do this, the Submit a Storm Report form will pop up. The final thing you have to do is enter the information and click Review Report and submit it. Then it's off to our office with that report. One thing to note is that it says Spotter ID in the contact section at the bottom of the form, but it is not necessary to input that kind of information. Feel free to use this form to submit any kind of significant weather, including fog or snow. We won't talk about that right now since it's actually finally warm. Thank you for watching, and we want to also thank everyone that again submitted storm reports and storm photos to the National Weather Service during these severe weather events. Again, this is the first time we've used this format for recapping a severe weather event, so please let us know what you think about it. We'd really appreciate the input. Thank you and have a great day.